When we deal with dipole moments, we're talking about polar molecules, or molecules that have a center of positive charge and a center of negative charge. And they're sometimes referred to as dipolar. So when we look at an example, hydrofluoric acid has a difference in electronegativity between hydrogen and fluorine. Not enough to transfer electrons and form ions, so they're going to have to share pairs of electrons. But fluorine has a higher electronegativity than hydrogen has, so it's going to pull on those electrons more strongly than the hydrogen and form a dipole moment. The dipole moment is going to go towards the direction of the fluorine. So hydrogen is going to be partially positive and fluorine is going to be partially negative. Any polar bond will show a dipole moment. So let's look at some more molecules. Let's draw the dipole for water and then for ammonia. So let's look at water first. We've got a hydrogen atom, polar covalently bonded to oxygen, and we've got a second hydrogen atom, polar covalently bonded to our oxygen. Since oxygen has a greater electronegativity, the pair of electrons that are being shared between each hydrogen and oxygen are not being shared equally, but they're going to be pulled closer to the oxygen atom. Not enough to form ions, but enough to give us polarity, a center of positive and a center of negative charge in our molecule. So our dipole moment would be going towards our oxygen atom. If we were to look at an ammonia molecule, we've got a polar covalent bond between each of the hydrogens and nitrogen. Nitrogen has a greater electronegativity than the hydrogens do, so the pair of electrons are not going to be shared equally between each hydrogen and nitrogen, but the nitrogen is going to have a greater attraction for that pair of electrons. That's going to give us polar covalent bonds and a polarity in the molecule. Our dipole moment for this particular molecule is going to be in the direction of the nitrogen atom, so we'll have a partially negative end and a partially positive end to our molecule. When are bonds polar, but molecules show no dipole moment? Well, this occurs when individual bond polarities are arranged in such a way that they cancel each other out. As an example, if we were to look at carbon dioxide, it's a linear molecule, so the polar bonds are going to cancel. If we look at sulfur trioxide, it's a polar molecule, so again, each of the polar bonds are going to cancel out. And if we have a tetrahedral arrangement, we're going to see that the polar bonds cancel out. So let's look at carbon dioxide as our example. We're going to have a polar covalent bond between each of the oxygens and carbon. The oxygens have a greater attraction for electrons, so we're going to have polarity between the oxygens and carbon. But the atoms are arranged in such a way in the molecule that those polar bonds are going to cancel out, and the molecule itself has no dipole moment. Let's deal with some ions and relate electron configurations to size. What is a stable compound? Usually the atoms of a compound achieve noble gas electron configurations by either sharing or transferring electrons, and in doing so, the compound becomes stable. So if we have two nonmetals, or two atoms on the right-hand side of the periodic table, they're going to form covalent bonds and share pairs of electrons between them. And when they share those pairs of electrons, they're going to complete their valence electrons to give them a noble gas electron configuration. The atoms and the molecule will become stable. If we have a nonmetal and a metal, something on the left side and the right side of the periodic table, we're going to form ionic bonds. And our ionic compound is going to be a stable compound when electrons are transferred from the metal to the nonmetal to give stable noble gas electron configurations. Now, ionic compounds are usually in their solid state, and the ions are close enough together that the repulsions are minimized and the attractions are maximized. In ionic compounds, the charges that the ions like to form make them stable with a noble gas electron configuration. So we want to deal with ion size. It's important to determine the structure and stability of ionic solids and the properties of their ions. So let's look at relative ion size, and it's related to relative atomic size. Positive ions are formed when electrons are removed from neutral atoms. And what ends up happening in this case is that the resulting cation will be smaller than the parent it was formed from. For negative ions, electrons are added to neutral atoms. So the anion will be larger than the parent atom it was formed from. And we've got a trend on the periodic table. Ion size increases as we go down a group, as does atom size, because we're adding energy levels. And it's kind of difficult to tell what the pattern for ions are as we go across a period, because we're losing electrons on the left side of the table, but we're gaining electrons on the right-hand side of the table. So if we look at this particular graphic and we look, let's say particularly at alkali metals, we've got a lithium, sodium, potassium, rubidium ion, and we notice that the ions get larger as we go down the group. And that trend follows across all the groups on the periodic table. And again, the reason for that is we're adding more energy levels, so the ions are getting larger. But as we go across a period, we're going to notice that for the metals, the ions are getting smaller, but for the nonmetals, they get large and then they get small again. And that has to do with the fact that we're losing electrons on the metal side, whereas we're gaining electrons on the nonmetal side. Let's deal with what are called isoelectronic ions. Iso means the same. So when we look at isoelectronic ions, they're ions that have the same number of electrons. And we want to remember this term because oftentimes we're asked to list ions by their size. And usually the ions are isoelectronic ions. So let's consider the neon series. Neon has 10 electrons in its electron configuration. So in the neon series, we're going to be looking at ions that also have 10 electrons. So oxide, fluoride, sodium, magnesium, and aluminum are all considered to be isoelectronic to neon. Now, when we look on the periodic table, we can find out how many protons are in the nucleus of each of these ions. So we look at the atomic number, and it tells us that oxygen has 8 protons, fluorine has 9, sodium has 11, magnesium has 12, aluminum has 13. When we look at the electrons in the atoms, that would be the same as the number of protons, but these are ions. So when we figure out the number of electrons in each of these ions, we're going to notice that they all have 10 electrons, which again makes them isoelectronic, and in the neon series because they contain the same number of electrons as the noble gas neon. Now, if we were to ask to arrange these ions by size, it's not the number of electrons or the number of energy levels that's going to help us determine the size, but it's the effective charge on the nucleus. As we go from oxide to fluoride to sodium to magnesium to aluminum, the number of protons in the nucleus increases, so the effective charge increases, which means that the electrons are going to be drawn in closer to the nucleus. So oxide would be the largest out of all the ions, whereas aluminum would be the smallest for all the ions. The ions with more protons will always be the smaller ions.